Hi, the topic is KMP algorithm. KMP algorithm is used for pattern matching. If a string is given and a pattern is given, then the problem is to find out whether this pattern is existing inside this string or not. If it is there, then find out its index. Now for this problem, there are various algorithms where KMP is also one of the algorithm. There is also a basic algorithm, naive algorithm. So let us look at how naive algorithm works. Then we can understand the problems or the drawback of naive algorithm. Then we'll see how KMP is better than basic or naive algorithm. Let us see the basic algorithm. See, if there is a string given and we have to find out this pattern, then we will check if it is there or not. So we'll start from the first letter of a string. So I'll write on this pattern here, D, E, F. Compare the first letter of a string with the pattern. It's not matching. If it is not matching, then shift the pattern to the right by one step, D, E, F. Now compare this one with this. It's not matching. Then shift the pattern by one step. This is not matching, so shift the pattern by one step. This is matching. If there is a match, no need to shift. Check the next. That is also matching. And check the next. This is also matching. So yes, a pattern is found inside the string at this place, at this index. That is 4 to 6 index. This example was very simple. I'll take one more example and show you. Now one more example. Here this is a string and the pattern that I have to search is this one. So I have to find out whether there is a match for this pattern in this string or not. So I'll not draw a string and shift it, but instead of that I will take index I and J here. So first letter I and J, this is matching. There is a match. So move J as well as I. So I'll just write I and J. They are matching. So move J as well as I. They are matching. So move J as well as I. Again they are matching. Now move J as well as I. There is a mismatch. See, we started this pattern comparing from this position onwards. As I just now said that in the previous example I have shown you that if there is a mismatch, this pattern will move by one step. So there is a mismatch. So again J will come in the beginning, but what about I? I will start from this place now. Already we have started from the beginning A, now we'll start from B, that is index 2. So this is the problem in basic algorithm. Already I have reached till 5 and it is again shifted back. So I is shifting in the string. This is the waste of time. This is the extra work in basic algorithm. Now again we will start from here. So this means that we have started the pattern from here now, shifted the pattern to the right by one step. That is the meaning. So I came here again. There is a mismatch. So go to the next. So we'll start comparing from here. So it means we have moved the pattern from here onwards now. From here we'll be checking. So mismatch. There is a mismatch. Move I. There is a match. So move J as well as I. There is a match. Move J as well as I. There is a match. So move J as well as I. Now there is a mismatch. Mismatch means move J again in the beginning and bring I again on this part. See, just now we have started from here. Now we have to shift this one. So we'll start from here. So I will come at this place. So already it has checked 3 alphabet. So it should come back 3 alphabet. So J should start from here again. See, just now already we have checked these alphabets. We are checking them again. So this is the drawback of basic algorithm. We are repeatedly checking the characters in a main string. Let me finish it quickly. There is a mismatch. I is moved. There is a mismatch. I is moved. Now there is a match with AA. So in this way now if I continue, then I can find this pattern here available here. Every character will be matched till here, till here. So we learn one thing here, that the characters in the string are compared repeatedly. Whenever there is a mismatch, it is shifting I, backtracking I, or moving back I. So this backtracking of I we want to avoid. Let us see a worst case of basic or naive algorithm. Worst case of basic algorithm. I have a string and a pattern. Let us run basic algorithm on this one. I starting from here, j starting from here. There is a match. If there is a match, move I as well as j. See, we started from index 1 of string. Remember this. There is a match. So move I as well as j. So first I will move j and also I will move I. There is a match. So move j and also I. There is a mismatch. When there is a mismatch, move j to the beginning and move I to the second position. This is the starting point. Just now we started from here, then I should start from here now. Start from here again. Again start. This is matching. Move j, move I. Matching, move j, move I. Again AA matching. So move j and move I. AB is not matching. So again move j in the beginning and move I on the third place. In this way continue. See, the problem in this one is AAA is repeating. Why I should move? I should move just j one place and see that this is A, both are same. Just check that next alphabet is B or not. You don't have to move back and start again from the beginning because all these are same only. That's it. That's it. The basic algorithm doesn't study the pattern, doesn't observe what is there in the pattern. As blindly it is checking every alphabet and just shifting this pattern by one step in case of mismatch. As this is backtracking I, what is the maximum time it is taking? If the size of the string is n and the size of the pattern is m, then almost this pattern is repeatedly compared in the string and this will be m into n, order of mn time. So this is the time taken by basic algorithm or naive algorithm. Basic algorithm takes order of mn time. Now, can we study the pattern and reduce some time? Let us see what is the idea of KMP. There is some terminology used in KMP algorithm. First, let us understand that terminology. See, if there is a pattern given here, then we can find prefix or suffix of a pattern. So what does it mean by prefix of a pattern? We have to take the subset of these alphabets in a pattern, but we must start from the beginning of the pattern only. How many characters I should take in a subset? As many as you want. So I just take A. Okay, yes, it's a prefix. No, I will take A and B also. Yes, this is also a prefix. I want to take A, B, C. Yes, this is also a prefix. I will take A, B, C, D. Yes, this is also a prefix. All these are valid prefix. Then what about suffix? I have to take the subset of this string, but I should start from the right hand side only, right? And as many I want I can take. So let us start. Can I take C? Just C? Yes. Can I take B and C? Yes. B, C. Can I take A, B, C? Yes. A, B, C. Can I take D, A, B, C? Yes. D, A, B, C and more. But let us stop here. Now the idea of KMP is that inside this string, is there any prefix same as suffix? Let us see. A, do you find anywhere? No. A, B, A, B, A, B. No, it's not there. A, B, C. Yes, it's there. See, this is matching. So this is the prefix that is also there in suffix. Also there in suffix. So this is the observation what KMP algorithm will do on a pattern to avoid the number of comparisons. Instead of confusing with the prefix and suffix, I'll make it simple. Is the beginning part of a pattern is appearing again anywhere else in the pattern or not? That's what we have to observe. I'll take few examples and show you. Let us look at the pattern. And in KMP algorithm, for a pattern, we generate a pi table. That pi is also called as longest prefix, which is same as some suffix, that is LPS. We name it as pi or LPS, whatever the name you like. So How that table is prepared, I will also show you that. Just observe it carefully. Let us take first pattern. A, is it appearing anywhere else? Yes. Oh, B is also appearing. A, B. So this A, B is appearing here also. Then again A, B, again A is appearing here, you see. A as well as B is also appearing. Okay, both are appearing again. So what we do is, we'll prepare a table. We'll write 0, 0, 0, 0. This AB is matching with first and second. As I said, the indices we will start from 1, 2 onward. So this is matching with 1 and 2. This is not matching. This is matching with 1 and 2. This is not matching. This is the pi table. Now there is an algorithm. I don't want to show you that algorithm. I'm not tracing the algorithm. Simply I am showing you how to prepare it. If you trace the algorithm, you will get the same results. Next, let us look at this pattern. A, is it appearing anywhere? Yes, it's appearing. Oh, B is also appearing. So this is matching. So this is 1 and 2. Then A anywhere? Yes, it's appearing here. So BC also appearing. So these three are matching. 1, 2, 3. Rest of them are all zeros. This is a pi table. Now let us check. A, is it appearing anywhere? Here itself. So mark 1. A, is it appearing? Yes, it's appearing. The next alphabet? No, it's not same. A is appearing here. The next alphabet also matching, 2. Then rest all of them are zeros. What about this? A is appearing here, 1. And this A is also appearing. So from here if you take, this is matching with this 2. So 2. And these 3 are matching with this 3. So take 3. Then anywhere else, yes, A is appearing here. The next A is also same. So 2. And rest of all the values are zeros. So this is the base of KMP algorithm to prepare the table. Once you prepare the table, the algorithm is simple. Then I will take one example and show you how algorithm works. Let us look at the working of KMP algorithm. My explanation will be based on the tracing of an algorithm. So one thing you have to observe, that here in the string, we will not backtrack in the main string. So let us start the working. So this is a pattern. So first of all, prepare a pi table or LPS. So prefix table. A, this is appearing here. So this is 1. And the B is also there. So 2. Then the D is not matching here. So not just 2 alphabets are matching. So take this as 0, this and this all are zeros. So let me put it in a table like this. And also give indices 1, 2, 3, 4, 5. And also I will take one index 0 that will act as a starting point of a pattern. Now let us start. First alphabet I is there. Then where is J? Now it is not on the first alphabet. We will take it on 0. This is a special thing. You can start from here also, but the working will change a little bit. I am starting from 0. This is easy. Let us watch. J is on 0, I is on 1, first alphabet. Now compare this string of I with the pattern of J plus 1 being here. Check the next alphabet. They are matching. If they match, then move J as well as I. Now again compare string of I with the pattern of J plus 1, this alphabet. So wherever J is pointing, you try to check the next alphabet. Thus B is matching here. So take J on the next and I also on the next. Now this J plus 1, yes, this is matching. This is matching J plus 1. So move J as well as I. Now J plus 1 is B and I is B. They are matching. So move J as well as I. Now J plus 1 is not matching with I. So now there is a mismatch. What to do? Observe it carefully. When there is a mismatch with J plus 1 and I, then move J to this index 2. Bring J here. Move it here. This means that this AB is repeating. So AB came 2 times. So already we have checked 1 time. So maybe we have to start from here. So let us observe. Now J plus 1 with this one. Is it matching? No, still there is a mismatch. So again move J to this place. J is here. Now, is it a match with j plus 1? No, still there is a mismatch, but j is on 0, so we cannot move j further, so move I. So in case of mismatch, you observe that only j is moving, I is not backtracking. I has simply moved to the next alphabet. Let us continue. J plus 1 is a match with this I, so move j, move I. J plus 1 B and I is B, match, so move j and move I. J plus 1 and I, C, A, mismatch, so move j to this place, j. And still compare j plus 1 A and I, mismatch. Now there is a mismatch and even j is at 0, so we cannot move j further on the left, so just move I. Now here's this part you observe carefully. J plus 1 A, I, this is matching. Move j, move I. Just I'll mark here. Now j plus 1 is B and I, they are matching. So move j and move I. J plus 1 is A and I is A, matching. So move j and move I. J plus 1, that is B and I, they are matching. So move j and move I. J plus 1 is a D, but this is A. They are not matching. They are not matching. Then where to move j? At 2. 2. Then again compare. J plus 1 A. A. Match. Match. C. AB. AB. So AB, already this portion is AB and this is also there here. So we need not compare that. We can continue from this portion. Here this was a mismatch. You can again start from the beginning. Means we reach till here, means this AB have came 2 times. That came 2 times. So one time you can skip and the second time onwards you can continue checking. So j plus 1 is matched with that one. So move j, move I. J plus 1 match with that one. So move j and move I. J plus 1 is a D and I is also D. So move j and I is incremented. Now this is the end of a string. Actually this we have reached the end of a pattern. So there is a pattern available inside the string. That's all. This is how KMP algorithm works. Or the basic idea behind the KMP algorithm is that if the beginning part of a string is appearing again somewhere else in the string, then don't again compare the characters, right? Avoid the comparison. And don't move I back again like it was happening in basic algorithm. You might have observed that we were moving I only in forward direction. We never backtrack I. Then what is the time complexity of this KMP? See, the size of the string is n and the size of the pattern, if I say m. Then how many times we have gone through this? Only one time. How many alphabets? N. So n is the time taken for parsing through this string. Then for preparing a table we have parsed through this one. So how many alphabets here? M. So for preparing table M and for searching a pattern N. This is for a table, that is pi table, and this is for search. So the total time is M plus N. So this is one of the faster algorithm for pattern matching.